Hi everyone. So in this video we're going to learn about beta sheets. So in our previous video we learned about alpha helix structure of the protein, and now we're going to learn about beta sheets. So as we all know that the alpha helix structure was a very highly coiled structure, and it was a compressed structure, right? So it was a compressed structure. Now when I try to extend or pull the alpha helix structure, it's going to create a beta strand. So beta strand is nothing but an extended version of helix structure. So this is actually the beta strand. Now everything is going to be same, the backbone, everything is going to be same, like the we used to have the N C alpha and then C backbone, right? So this was actually the backbone of the protein. This is going to be same in beta strand also, except for the amino acids that will be contributing to its different nature. So we're going to learn about that as well, so don't you worry about it. So now let us see how does a beta strand look like. So as you can see that this is an extended version of beta strand. We have an N group towards the left side, and we have a carboxylic group towards the right side. As you can see that the R groups which are present in each and every amino acid is pointed outwards. That means this is pointed outwards, this is also pointed outwards. That means it is pointing towards the opposite direction. The reason why this is happening is because they have a very bulky group, bulky group of amino acid, due to which they don't want to create any kind of steric hindrance. Therefore the R group is pointing towards the different direction. Now if you see over here, this is just a beta strand, right? This is just one strand that we're talking about. But how is a beta sheet formed? That means beta strand is one single strand, and when we take two strands together, they are going to form beta sheet. So as you can see over here that we have two beta sheets over here, right? And then the reason why I call it parallel is because both the ends have the same terminal, right? It has N terminal, N terminal, C terminal, C terminal. Why am I calling it anti-parallel? Because one of the side has N and the other side has N, right? This is N. So the other side has N, and then in the other side we have C, and then we have C to the other side. So this is the anti-parallel. Okay, so now let us see how does these two beta strands are interconnected with one another. So I'm gonna show you how they interconnected with one another. So let us take the parallel beta sheet. So they are interconnected with one another by hydrogen bonds. So what the lines that I'm drawing over here is actually a hydrogen bond. Okay, and as you can see over here that the hydrogen bond is forming at at a certain angle, and it is an inclined angle. That means it is not a straight angle, it is like slightly inclined towards any direction. Now if I talk over here, this is the anti-parallel beta sheet. I'm going to draw a hydrogen bond over here as well. So as you can see over here that the hydrogen bond it is forming is actually a 180 degree hydrogen bond, right? This is also 180, this is also 180, right? So when we compare parallel beta sheet and anti-parallel beta sheet, there is a difference in the hydrogen bond formation. So out here the hydrogen bond is slightly inclined, it doesn't have a 180 degree. Out here it is straight, so it has a 180 degree. Now the hydrogen bond is formed between two beta strands, right? So what are we going to call it? Are we going to call it intermolecular or intramolecular? What do you think? We are going to call it intramolecular. Oh, sorry, not intermolecular hydrogen bond, right? Now, when we talked a hydrogen bond in terms of alpha helix, do you think it was intermolecular or do you think it was intramolecular in terms of alpha helix? It was intramolecular because the hydrogen bonds were forming between the same atoms, the atoms of the same compound, right? Of the same protein. So I hope you're able to understand this intermolecular hydrogen bond and the parallel and the antiparallel beta sheet. Now I'm going to show you a book diagram which will like make it more clear. So as you can see over here, this is the parallel beta sheet, right? And then we have the C terminal over here and then the N terminal over here, right? The C terminal over here and then N terminal over here. That means it is the same one, right? This is C N N, right? Now let us try to see what kind of hydrogen bond will be favorable in this parallel beta sheet. So I think this should be one of the hydrogen bonds. So between this carboxyl group and then this amino group, right? As you can see that the hydrogen bond is inclining to an angle, right? It is inclined. Now over here also, as you can see that this will be forming hydrogen bonds, right? And then this is forming bonds between two sheets, two strands. This is one strand and this is another strand, and they are forming bond between themselves, between two strands. Therefore the hydrogen bond is going to be intermolecular. Now you must be wondering that this is also one of the hydrogen bond that could be formed, right? So when we talk about in parallel beta sheets, not only inclined hydrogen bonds will be formed, but 180-degree hydrogen bonds will also be formed. But which will be more in number? The inclined ones will be more in number. Okay, this is the reason why the parallel structure of beta sheets is not favorable. That means it is not found much because it is not very much stable, because only the hydrogen bond which makes a 180-degree bond, that will be stable, right? So now let us take an example of antiparallel. So in antiparallel, as you can see over here, just a moment. Okay, so over here, this is the hydrogen bond, this is another hydrogen bond, this is another hydrogen bond, and then this is another hydrogen bond. So the inclined hydrogen bond is very less in number, as you can see, right? So the inclined is very much less in number, and then the most common hydrogen bond which is formed is 180 degrees. So the reason antiparallel is most common in nature is because it is most stable. Therefore, every beta sheet that will be formed will be usually antiparallel in nature. So this is the C end, and there should be like N end, and this should be the N end. This should be the C end. Okay, so I hope you're clear about the parallel and the antiparallel sheet. Now, one of the things that I want to talk about is which is the most common one, that is the anti-parallel beta sheet, right? Another thing is that when we talk about the side group which I was talking about. If you remember, I talked about the side group, right? And I said that they are like, pointed outwards, right? So I talked about the R group, which was, pointed outwards. So as I said, that the reason why the R group is pointed outwards is because they have a very bulky, bulky side chain and aromatic, specifically like a benzene ring structure. So they have benzene ring. So they have a very bulky group, which is like, present in the R group. Therefore, it is present in the outward direction. Now let us see. Okay, so what are the major common amino acid which favors beta sheet? They are tryptophan, right? It's tryptophan. This is tyrosine, and then phenylalanine, right? Now, we have some other details to know as well. So when we talk about the pitch, so we all know that what exactly is pitch, right? So pitch is actually one turn. So when we talk about turns, what is the measurement of the turn? So when we talk about the turn, it is 6.4 angstrom. And then when we talk about in anti-parallel, it is 6.8 angstrom. That means in parallel the pitch is 6.4, and then in anti-parallel it is 6.8. Now if I have to if I have to know that how many amino acid is present per turn, like in one turn, how many amino acid is present, that means there are 2 amino acids. Now by by looking at these data, will I be able to find out the axial height of the amino acid? You know what is axial height, right? If you don't know, you must watch my previous video on alpha helix. So the delta Z is actually the axial height. Now what exactly is axial height? I'm just going to give you a small thought. So if this is a helix, right, and then if there are there are amino acids over here, and then if one is over here, let's say. Now if I want to know the distance between them, that means this is one of the distance, right? This is one of the distance height, and this is the other height. So the height, the vertical distance between, so if I talk about the axial height, then the distance between these 2 amino acid is actually the axial height, right? And it is also known as rise per residue. That means what is the exact amount of rise from one amino acid to the other one. So this is actually the axial height. I just wanted to give you a recap. So the Z that I have written out here is actually the axial height. Now we know what the pitch is, right? And we know the number of amino acid per turn as well, that it will be 2. Now if I want to find out the axial height of parallel beta sheet, then how much it will be in parallel beta sheet? Let's take this one. So in parallel beta sheet, the Z will be, I just have to divide it, right? So it will be 6.4 divided by 2, because 6.4 is the pitch and 2 is the amino acid per turn. So that will be approximately 3.2 angstrom, right? And then what about anti-parallel? So when we talk about anti-parallel beta sheet, the axial height will be 6.8 divided by 2, right? So here will be 6.8 and here will be 2. That will give us 3.4 angstrom. Okay, so I hope you're clear about these data. Now let us move forward to the type of hydrogen bond. I already discussed the type of hydrogen bond, this will be intermolecular hydrogen bond, but still I'm going to write it down. The reason why it's called intermolecular hydrogen bond is because it is forming between two beta strands, right? And the reason why we are calling the alpha helix an intramolecular hydrogen bond is because the hydrogen bond was forming between the same alpha helix structure. So in this video we learned about the beta sheet, right? And we know that the beta sheet is actually the extended version of helix, and they are going to have the same backbone, that is N-C alpha C, and then the R group is pointed outwards because of the bulkier amino acids tryptophan, tyrosine and phenylalanine, which is present in the R group, right? And then also the hydrogen bond which is made in the parallel beta sheet is actually an inclined one, but there is a possibility that 180-degree hydrogen bonds can also be formed, but most of the common ones are the inclined ones. And in antiparallel we have the 180-degree hydrogen bond, which is the most stable form of hydrogen bond. Therefore antiparallel beta sheet is favored by the nature. As I told you that over here also we could see the book diagram, and then I showed you how inclined hydrogen bonds are formed. The most common hydrogen bond is anti-parallel beta sheet because 180-degree. Most common WIF, these are the 1-letter code for amino acids. And then we talked about the pitch, parallel, anti-parallel, angstrom, and then how many amino acids are there per turn, and then what will be the axial height for parallel and anti-parallel sheet. So if you like this video, please like, share and subscribe. Thank you so much for watching, guys.